Hey guys, Miss Marusik here, and in this video we're going to talk about calculating with equilibrium expressions utilizing a rice table. Now, what we're going to talk about in this video is kind of a foundational piece for us to be able to do all the calculations that we do throughout this unit. So keep that in mind. You want to really make sure you understand how to utilize rice tables in calculations after watching this video, because we're going to be seeing it over and over again throughout our next several videos. With that said, I want to kind of back up for a minute and talk about reactions up to this point. Anytime we've done calculations with reactions in the past, we have always assumed that however much reactant I have ends up, for the most part, all becoming product unless it's in excess, and I could use stoichiometry to do those calculations. The problem is that with equilibrium, I'm not going to necessarily transform all of my reactant into product. I may only transform a portion of it before that reverse reaction is going to kick in. I might even be given in the problem a little bit of both reactants and products and asked about how things shift around. It gets a lot more complicated when you're talking about equilibrium. And so therefore, it's really important to organize our information so that we know what kind of pieces we're dealing with. And that's where a rice table comes into play. Now, the acronym of RICE stands for reaction. So we're going to write our balanced equation, initial concentrations, change in concentrations, and then equilibrium. What do we have once those rates stabilize out? So there's where our RICE comes into play. And what they do is they basically just help us organize information so that we can kind of start to figure out what is happening where. Now, something we have to keep in mind, you notice that they did mention concentrations here. That is because only molarity or pressure values can go in a rice table. So if you're given moles and volume, you're going to have to convert that into a molarity before you put that information into a rice table. So be very careful with that. Now there's some other guidelines on here. We're not going to look at all of them in this video. We're going to save some of those for next class. But to kind of give you some of the highlights, we're going to be given some initial concentrations of substances. It can be initial concentrations of both reactants or of products even. And if an initial concentration or pressure is not given, then we assume it's starting to be zero. And so then we can kind of start from that information to evaluate what would change. However, something to keep in mind is that any changes that occur will happen in mole-to-mole relationships. So if there's like a 2-to-1 ratio between two substances, then those changes are also going to be in that 2-to-1 ratio. And so we're going to need to use our coefficients in order to determine what appropriate changes would take place. If we don't know what a change is, or we don't know, say, what a final concentration might be, then we can use X to represent any kind of unknown values. Now, we will have to be careful because, again, if we are dealing with mole-to-mole ratios, we might have something changing by X and something else changing by 2X. And so we'll need to address that as we set up our stuff here. Also, it says if one of the sides is completely lacking in a reactant or product, the reaction will shift to create some more of that substance. So like, let's say we're starting off with all reactants and there's no products. Well, obviously some of those reactants are going to need to shift to the product side for that reaction to take place. Now, if we aren't given a side that has nothing available, then we might have to do a little bit of extra work to figure out how that reaction is shifting. And that's something that we're going to conquer in another video. So on this step 8 here, that's something that we're going to do later on. Finally, what we would do is we would substitute our final concentrations into an equilibrium expression and solve whatever they're asking me to figure out. A lot of times they are asking you to solve your equilibrium constant, but they could ask you to solve an unknown concentration when they give you what that equilibrium constant is. So there's all kinds of ways that they could ask these questions. And so we're going to see several examples of that as we go through today's video. So with that said, let's go ahead and flip the page and start looking at some examples. So to start off with this first one, it said, hey, at a particular temperature, I have a 3-liter flask that contains 3.5 moles of HI, 4.10 moles of H2, and 0.3 moles of I2 at equilibrium using this reversible reaction here. Now, that key word there of at equilibrium tells us that these are what we have at the end of the process once those rates have equaled out. So we don't have to worry about having initial stuff that we're trying to shift around in order to get to that end. We are already at that equilibrium state. So with that said, I'm going to start organizing my information in a rice table. So I started off with my R here and writing my balanced reaction. Now my I and my C, I'm going to leave those blank here because, again, they are already telling me my values at equilibrium. So I don't have to worry about figuring out how things are going to shift around. These are the values that I would use at the end. Now, at equilibrium, though, remember we said we can only use molarity or pressure in these rice tables because I can only use molarity or pressure in my Kc expressions. And so therefore, I needed to do moles over liter for each of those to figure out what those equilibrium molarities would be. So then at that point, I would go write my Kc expression. I know Kc is products over reactants raised to their coefficients. The Hi, our product, was raised to an exponent of 2 here because of its 2 coefficient, but my 2 reactants were just raised to 1 and 1. So now that I have those ending molarities, I can now plug them in for those concentrations here and simply solve. Now you notice I did use 3 significant figures throughout. That was because all of the initial values they gave me had 3 significant figures. And so that got me a final Kc value of 9.99. The final question for this one asks, does equilibrium lie more towards the reactants or products? Well, I see here that this is greater than 1, so that would indicate I have an abundance of products in comparison to reactants. And so I would say that equilibrium lies to the product side of the reaction because, again, that equilibrium constant is greater than 1. Now that one wasn't too bad because, again, I didn't have any kind of changes that I had to worry about. All the values that they gave me were already at equilibrium. And we're going to see that same thing on our next question here. So for this one, it says, hey, in another trial involving the same reaction from the previous example, the temperature was changed to 448 degrees Celsius. At the new temperature, they give us a new equilibrium constant of 50.5. So while I'm not going to use that 448 degrees Celsius in my work, it's just to let me know that, hey, because I have a new temperature, that equilibrium constant is going to be different than the 9.99 I previously calculated. So then it says, hey, we have an equilibrium mixture at 448 degrees Celsius, meaning we're already at equilibrium with these values. And so what they want us to do is to calculate the concentration of Hi in this mixture. So again, I'm going to utilize that rice table to organize the information that I know. So in setting up my rice, I see my R is my reaction, and then I say, hey, these were already at equilibrium, so let me go ahead and put those in for E down here, for the H2 and the I2. However, I don't know the Hi, and so I'm going to put a placeholder of X there to represent this value I don't know. So then, it told me that the Kc value was 50.5. So once I set up that Kc expression again, just the same as I did up above, because it's the same reaction, I would have 50.5 plugged in for Kc. My X is going to get plugged in here for Hi, and that's going to be squared over my 2 concentrations for H2 and I2 at equilibrium. And so then all I'm doing at that point is just solving for X. So what I did is I multiplied the 0.575 and the 0.375 over to the side with 50.5. Once I multiplied all those 3 together, that got this 10.88906 number. That would equal X squared. And so then, of course, to undo the squared, I would square root both sides. Or, remember, square rooting is the same thing as raising to an exponent of 1/2. So if you had something other than 2 here, like if you had 3 or 4, you would just raise both sides to 1 over that number in order to undo that exponent. That got me that my X value, which is my Hi, is equal to 3.30. You notice I did put a unit here because this time I was calculating a concentration, and so we needed to put that this was molarity. So then it asks me a couple questions down here. It says, are the reactants or products more favored at equilibrium Well, that equilibrium constant was 50.5 for this one. So since that was bigger than 1, that means that the products are more favored at equilibrium, just like we did in our previous videos. So then on this one, this is a throwback to our video right before this. It says if the reaction was written in the reverse direction, so instead I had 2HI going back and forth between H2 and I2, what would be the reported value of Kc? And as we recall, reversing the reaction ends up inversing our Kc value. And so then I could just do 1 over that 50.5 to figure out what my equilibrium constant would be for this reaction as written. All right, now on both of these, we didn't have to worry about the initial and change components because the values that they gave me were already at equilibrium. Let's look at some where that does change, that they do give me values of initial concentrations of things that then I'm going to have to figure out what's changing. So let's go ahead and look at the next two examples. So on this one here, it says, hey, I have phosphorus pentachloride gas decomposes to form chlorine gas and phosphorus trichloride gas. Now, I notice on this one off the bat that they did not give us a balanced reaction, that's something we're going to have to write. And so that was the first thing I did in kind of utilizing my rice table, is I went ahead and said, hey, PCl5, phosphorus pentachloride, goes back and forth between Cl2, chlorine gas, and PCl3 phosphorus trichloride. And luckily for us, that reaction comes out already balanced in 1-to-1 coefficients. So then, I keep on going. At a certain temperature, a 2-liter flask initially contained 0.298 moles of PCl3 and 0.00870 moles of PCl5. Now you notice they very clearly said here that that was initial concentrations of those things. And one other thing to point out is they're giving me moles here and a volume. And if you recall, we said in a rice table, we need to put molarities. So what I did is I said, okay, I've got some initial concentrations here, but they're not yet in a concentration. So let me take my moles and divide it by my liters and get a molarity for PCl5. So that's what I did here. I took that 0.00870 and divided it by 2. And then I did the same thing for the PCl3 here on the product side. I took that 0.298 and divided it by the same 2 liters to get my molarity. Now you notice they did not mention at all having a starting concentration of Cl2. They didn't even mention it at all. So the assumption would be that it starts out at 0. That is the assumption. If we do not see an initial concentration mentioned for a substance, then we assume that it starts off at 0. Now, we can't make that assumption at equilibrium. I should have a little bit of each at equilibrium. But for initial concentrations, if it's not mentioned, we assume it to be 0. So then it says, after the system had reached equilibrium, so that means down here, E, now I have 0.002 moles of Cl2 found in the flask. So now I have that 0.002 moles in the 2 liters, and so that would be a molarity of 0.001 molarity for the Cl2 at equilibrium. Now, it wants us to eventually calculate the equilibrium constant Kc for this reaction. Well, to plug into Kc here, which I went ahead and wrote my products over reactants here, I need at equilibrium what the value of PCl5 and PCl3 would be. I have Cl2 at equilibrium. I know what I can plug in there, but I don't have these other 2 substances. And so that's what I've got to work to try and figure out. Now, you notice I wrote something here in orange. I wrote that I know that the Cl2 started at 0 and went up to 0.001 molarity. So the increase here, the change of Cl2, was 0.001 molarity. Well, let's think about this. I have mole-to-mole ratios here between these. I have a 1-to-1 ratio between Cl2 and these other 2 substances. So if Cl2 went up by 0.001, that means these other 2 guys changed by 0.001. However, I've got to be careful about how they're changing. The PCl5, if I'm producing some of that Cl2, for Cl2 to go up, that means the PCl5 is going to need to go down. It's going to need to use some of that up in order to make more product. However, in making more product, this PCl3 that I had would also increase. If I take some of that reactant to make product, I'm going to make some of both products here. But again, I'm going to do so in mole-to-mole ratios. So I'm going to put up a little bit more information than what I wrote here. This is all the information that I would have kind of put down initially that I knew based off the problem. And so then here's where then I would kind of start to think about, okay, how is everything else changing? And so that's where I get to here. So once I say that, hey, this had to go up by 0.001 molarity, that means our PCl5 here had to go down by that same value because, again, a 1-to-1 molar ratio. So it went down by 0.001 molarity. And if it started at 0.00435 and it goes down by 0.001, then that would bring it down to 0.00335 molarity at equilibrium. So then on the other side here with PCl3, again, that product side is increasing, but again, 1-to-1 molar ratio. So that means our PCl3 is also going up by 0.001 molarity. And if it started at 0.149 and it's going up by 0.001, that would bring me to a final molarity at equilibrium of 0.150 molarity. So now that I have all of these equilibrium concentrations, now I can plug those in over here into Kc. And so you notice I plugged in the Cl2, the PCl3, and the PCl5 values that we had here at equilibrium, and that got me a Kc value of 0.0448. Again, no unit. Also, I know because this is smaller than 1, that this must have been reactant favored at equilibrium. So, and again, all those questions that we've seen kind of throughout the course of this unit so far, I can now be asked now that I know what the Kc value is. All right, let's look at one more problem that's kind of similar. This one says sulfur trioxide gas decomposes at high temperature in a sealed container to produce sulfur dioxide gas and oxygen gas. The reaction is an equilibrium system. So the first thing I did is, again, I wrote myself a balanced reaction here. And again, it told me it's at equilibrium, so I put my two-way arrow. And I see that I'm starting off with 2 SO3, sulfur trioxide, to decompose into sulfur dioxide, SO2, and I need 2 of those, and then O2 as a gas. And you notice I did put gases on all of these just to remind me that they would get included in an equilibrium expression. If you don't put the states, is it that big of a deal? No, as long as you know what gets included in your equilibrium expression and what doesn't. So just be careful on that. So then it says, hey, initially the vessel is at 1,000 Kelvin, so they're just giving us the temperature there, with SO3 at a pressure of 0.5 atmospheres. So we see here they're using pressures instead of concentrations, which will slightly change how we write our equilibrium expression here in just a minute. So then it says, hey, at equilibrium, the total pressure in the reaction vessel is 0.650 atmosphere. So that means all of these pieces at the end are going to add up to 0.650 atmospheres. And what they want us to do is to calculate the pressure of all 3 gases in the vessel at equilibrium. Now you notice they did not mention the pressure of SO2 and O2 at the beginning of this. They didn't mention an initial pressure. So again, our assumption would be that those are both starting off at 0. And that's important because what that means is throughout the course of this reaction, if this side is starting at 0, these concentrations are going to have to go up. But that means this pressure is going to have to go down. And so that's going to help me kind of figure out what those changes are. Now I am going to go ahead and show you kind of where we're going with this problem. The whole idea of getting these ending pressures at equilibrium is so that I can do part B. Part B wants us to write the equilibrium pressure constant expression for this reaction. Now you notice here they're saying pressure constant, the Kp, and we want to use it to calculate the value of Kp at 1000 Kelvin. So remember with Kp, I don't use brackets. It's not molarity here. And so I want to put those pressures in parentheses, but again, I do raise them to their exponent that's equal to their coefficient. So same idea, products over reactants, except that I want to use pressures in parentheses instead of brackets for molarity. So just be careful with that. So now let's kind of go back here and talk about what information could I now plug in. Well, as we said, if we have no product, these are going to both have to go up, and this reactant here is going to have to go down. But I also notice I have a 2 to 2 to 1 ratio. So those ratios of changes are going to maintain that 2 to 2 to 1 ratio. So let me go ahead and put up here what I did for my next steps. So what I said here is that, hey, this SO3 is going to have to go down. And it's going to go down by some value I don't know, X, but it's going to be in a 2 to 2 to 1 ratio. So I'm going to say it's going to go down by 2x. The SO2 is going to go up because, again, we're going to shift over to that product side, but it's going to do so by 2x because, again, that coefficient of 2. Whereas O2 is just going to go up by x. And again, the whole reason why we know these go up is because if we have no products, products have to increase and the reactants have to decrease. That's the whole reason why I know I'm shifting in that direction. Now, next class, we're going to talk more about what do I do if I don't know which direction off the bat to shift in? How do I know that I'm shifting towards reactants or products? So if you're confused by that, hold on to that thought. I promise we're going to kind of conquer that here in an upcoming video. So with that said, at equilibrium, I would have 0.5 minus 2x for the pressure of SO3 at equilibrium. I would have 2x for the pressure of SO2 at equilibrium, and for O2, my pressure would simply just be x. And as we said, the total pressure is 0.650. Now, this utilizes the idea of Dalton's law of partial pressures, that these individual pressures should add up to give me the total pressure. So yes, you might see a little gas laws or other topics thrown in here, which kind of throws us off. So what we would do is we would simply just take these three equilibrium values, add them up to give me by 0.650, and then I would end up solving for x. As you notice, the negative 2x and the positive 2x would cancel out, so that would leave me with 0.5 plus x equals 0.650. And so then, to rearrange for x, I would simply subtract 0.5 from both sides, and that gets me that my x is 0.150. So now, if I want those ending pressures of all three of these gases, I would just apply this x value to these equations I wrote in here. We said that SO3 is equal to 0.5 minus 2x, and if x is 0.150, then that would give us a final pressure for SO3 of 0.2 atmospheres. For SO2, we said that it was equal to 2x, so 2 times the 0.150, so that would give me a final pressure of 0.3 atmospheres. And then finally, for O2, it had a pressure of x, and so therefore its equilibrium pressure would just be the 0.150. So here's the deal. I now know what these equilibrium pressures are. And so what that means is that I can come down here to part B and plug in those values in order to solve my Kp. So all I did now is I said, hey, SO2 was 0.3. That's going to get squared because of its coefficient. O2 is going to be 0.150. The pressure of SO3 was 0.2. Again, it was squared because its coefficient was 2. And so that gets me a final Kp value of 0.338. And again, just like Kc, Kp does not have a unit. It's just a simple ratio there. All right, I hope we're feeling good about kind of getting used to what a rice table can help us do and organizing that information. Like I mentioned earlier, here in our upcoming videos, we're going to be doing a lot more with rice tables. We're going to be looking at how do I know which way to shift equilibrium if I have a little bit of both reactants and products. We're going to be looking at utilizing this for Kas and Kbs for acids and bases. We're going to be utilizing these for Ksp for salt solubility. So all kinds of good things coming with rice tables. But the key thing I want you to remember is that if I have equilibrium, I use a rice table. If I don't have equilibrium, if I assume my reaction goes to completion, then I use stoichiometry. So that's kind of our two key ways that we calculate amounts with regards to reactions. All right, if you have any questions or need any help, please feel free to email me. Bye, guys.